In the unending, silent blackness between galaxies, time itself seems to lose its meaning. Across this unfathomable void, a story is written in the ancient light of long-dead stars. It is the grandest of all narratives, the autobiography of existence itself. Yet, for eons, the opening chapter of this cosmic saga remained lost, a formless whisper from an age so remote, so utterly alien, that the universe itself seemed to have forgotten its own birth. A profound amnesia had settled over reality, shrouding the first moments after creation in an impenetrable fog. We could see the faint afterglow of the beginning, a baby picture of the cosmos, and we could see the grand, structured galaxies of its maturity. But the infancy, the toddler years, the transition from a uniform, hot plasma to the first sparks of organized light that was a blank page, a lost memory, until now. Suspended in the absolute zero of deep space, a million miles from the world that built it, humanity's most ambitious eye has been staring into that primordial darkness. The James Webb Space Telescope is not merely an observatory, it is a time machine constructed of gold and beryllium, a technological marvel designed for one transcendent purpose: to capture the ghosts of the beginning. And in the faint, stretched-out photons that have travelled for over 13.5 billion years to reach its golden mirror, Webb has found it. Not a star, not a galaxy, but something far more elemental, far more profound. It has discovered a pristine, untouched fossil from the dawn of time. Webb has just located the universe's lost memory. To comprehend the magnitude of this revelation, we must first journey back, not just a few million years, but to the very precipice of time. Imagine the universe, a mere 380,000 years after the Big Bang. It was not the star-dusted cosmos we know today. It was a seething, opaque cauldron of ionized particles, a fog of protons and electrons so dense that light was trapped, bouncing endlessly like a ball in a cosmic pinball machine. Then, as the universe expanded and cooled, a monumental event occurred. The fog cleared. Electrons and protons combined to form the first neutral atoms, primarily hydrogen and helium. For the first time, light was set free, released in a brilliant flash that still echoes through space-time today as the cosmic microwave background radiation. But this liberation of light plunged the universe into a new kind of darkness. This was the dawn of the cosmic dark ages, an epoch of profound silence and gloom that lasted for hundreds of millions of years. The universe was now transparent, but there was nothing to see. There were no stars to illuminate the void, no galaxies to swirl in majestic spirals, no planets, no life. There was only an endless, expanding ocean of neutral hydrogen and helium gas, suffused with the enigmatic presence of dark matter. This vast, featureless expanse was the forgotten childhood of our reality. The laws of physics were in place. The ingredients for everything that would ever exist were present, but the cosmic kitchen was cold and dark. The great story of stellar evolution, of galactic formation, of life itself, had not yet begun. The universe held its breath, waiting for the first spark. The quest to witness that first spark, an event astronomers call the cosmic dawn, is what drove the creation of the James Webb Space Telescope. For decades, we have been haunted by a fundamental question. How did this uniform, boring gas cloud of a universe transform into the complex, glittering tapestry we see today? The theoretical answer was the formation of the very first stars. These were not stars like our sun. They were mythological beasts, titans of a bygone era, known to science as population 3 stars, forged from nothing but the pure, unadulterated hydrogen and helium of the Big Bang. They were immaculate creations. Without the heavier elements that contaminate modern stars, they could grow to colossal sizes, hundreds, perhaps even 1,000 times the mass of our own sun. Because of their immense mass, these primordial stellar furnaces burned with an almost unimaginable intensity. They were millions of times brighter than our sun, blazing with a fierce blue-white light. But this brilliance came at a cost. They lived fast and died young. While a star like our sun will burn for 10 billion years, These first-generation giants exhausted their fuel in a mere 1 or 2 million years. Their deaths were not quiet affairs. They exploded as titanic supernovae, cataclysms of such violence that they seeded the surrounding cosmos with the first heavy elements, the first traces of carbon, oxygen, and iron. These explosions were the anvils upon which the building blocks of planets, and ultimately of life, were forged. These first stars were the crucial link, the entities that ended the cosmic dark ages and began the process of enriching the universe. They were the memory we needed to find. But finding them is an almost impossible task. They are gone. They all died out more than 13 billion years ago. We cannot see them directly. We can only hope to see the light from the first galaxies they coalesced to form. Even this is a challenge of staggering proportions. The universe has been expanding for 8 billion years. Light from these nascent galaxies has been traveling across this stretching fabric of space-time for almost its entire existence. As space-time expands, it stretches the very wavelength of the light traveling through it, a phenomenon known as cosmological redshift. The brilliant ultraviolet light of those first stars has been stretched so profoundly that by the time it reaches us, it is no longer visible light. It has been transformed into the faint, long wavelengths of infrared radiation. The Earth's atmosphere is opaque to most of this ancient infrared light. To see it, to capture these whispers from the dawn of time, you must go to space. More than that, your telescope itself must be incredibly cold. Any heat from the instrument would create an infrared glow that would blind it to these faint cosmic signals, like trying to spot a firefly in the glare of a searchlight. This is why the Hubble Space Telescope, a revolutionary instrument in its own right, could only peer back so far. It operated in a relatively warm environment and was optimized for visible and ultraviolet light. It could see teenage galaxies, but the infant universe remained hidden in the infrared haze. Enter the James Webb Space Telescope. It is an engineering masterpiece, a monument to human ingenuity designed to conquer these exact challenges. Its primary mirror, a breathtaking mosaic of 18 hexagonal segments of beryllium coated in a microscopically thin layer of pure gold, spans an incredible 6.5 meters. Gold is an exceptionally efficient reflector of infrared light, making this honeycomb structure the perfect eye to capture the universe's earliest photons. To keep this sensitive instrument cold, unimaginably cold, it is protected by a 5-layer sunshield the size of a tennis court. Each layer is thinner than a human hair, and together they dissipate the sun's heat, creating a permanent shadow that allows the telescope to passively cool to a staggering -233 degrees Celsius, just 40 degrees above absolute zero. This entire colossal, delicate observatory was folded like a complex piece of origami to fit inside a rocket fairing. It then journeyed for a month to its lonely outpost, a gravitationally stable point in space known as Lagrange Point 2, a million miles beyond the Earth's orbit. There, far from the heat and glare of our world, it slowly, meticulously unfolded itself, each step a potential mission-ending failure. But it succeeded. And once it cooled, aligned its mirrors to a precision of nanometers, and opened its golden eye, it began to do what it was built for, to stare back into the abyss of time and hunt for the universe's lost memories. The initial discoveries were astonishing. Webb began finding galaxies, countless of them, that were far more mature, far more structured, and far more numerous in the early universe than any of our models had predicted. It was like looking into the distant past and finding a photograph of a shockingly well-developed infant. This presented a profound puzzle, suggesting that the story of cosmic evolution was more rapid, more violent, or perhaps just different than we had imagined. But even these remarkable discoveries were, in a sense, secondary. They were the evidence of the memory, the consequences of the first events. They were not the memory itself. The true Holy Grail was to find a direct, physical remnant of the era, times before times the first stars had polluted the cosmos with heavy elements. And then it happened. While observing a distant quasar, a superlatively bright galactic nucleus powered by a supermassive black hole, a team of astronomers noticed something unusual. They were not studying the quasar itself, but rather using its intense light as a cosmic backlight, like a flashlight shining through a fog. As the quasar's light traveled across billions of light-years towards Webb, it passed through whatever lay in its path, and every cloud of gas it traversed would absorb certain specific frequencies of light, leaving a unique fingerprint, an absorption line, in the quasar's spectrum. By analyzing these fingerprints, astronomers can deduce the chemical composition, temperature, and density of these otherwise invisible cosmic clouds. This technique is called spectroscopy, and it is the key that unlocks the chemical history of the cosmos. Imagine the full spectrum of light from the quasar as a perfect, continuous rainbow. When that light passes through a cloud of hydrogen, the hydrogen atoms absorb light at a very specific wavelength, creating a black line in the rainbow. If the cloud also contains helium, it will carve out its own distinct lines. If it contains carbon, or oxygen, or iron, each of these elements will leave its own unique, identifying barcode of black lines. For decades, astronomers have used this to map the distribution of matter across the universe. Every cloud they had ever found, no matter how remote, showed the telltale barcodes of not just hydrogen and helium, but also a smattering of these heavier elements, or metals, as astronomers call them. This was proof that the gas in these clouds had been processed, enriched by at least one generation of stars that had lived, died, and scattered their ashes into the void. But as Webb's sensitive spectrographs analyzed the light from this particular quasar, the data that streamed back to Earth was different. It showed a cloud of gas so ancient that its light had been traveling for over 13.2 billion years. As the team processed the spectrum, they saw the expected powerful absorption lines of hydrogen. They saw the faint telltale signature of helium, and then nothing. There was no barcode for carbon, no fingerprint for oxygen, no trace of silicon or iron. There was an eerie, profound silence in the spectrum where the signatures of all the heavier elements should have been. The initial reaction in the control room was one of cautious skepticism. It had to be a mistake, an artifact of the instrument, a glitch in the data processing pipeline. They ran diagnostics. They recalibrated the data. They had other teams independently analyze the results. The conclusion was inescapable. The data was real. The silence in the spectrum was genuine. They were staring at the chemical signature of a gas cloud that had never been touched by a star. It was a pocket of the universe that had somehow survived for hundreds of millions of years in its pure, primordial state. A direct, unadulterated sample of the material forged in the first 3 minutes of the Big Bang. This was it, the cosmic Rosetta Stone, a preserved fossil of the universe as it was during the cosmic dark ages. This cloud was not just a memory, it was a living piece of the universe's infancy, floating like a ghost in the modern cosmos. Its composition was a direct echo of the predictions of Big Bang nucleosynthesis, the theory that describes the formation of the first atomic nuclei. The proportions of hydrogen and helium were exactly what our models, formulated in laboratories and on chalkboards here on Earth, had predicted for the early universe. It was a triumphant confirmation of our fundamental understanding of cosmology. But this discovery does more than just confirm what we thought we knew. It opens a new window, presenting us with a tangible piece of the past that we can study in exquisite detail. This pristine cloud is a laboratory for understanding the very first stages of cosmic structure formation. How did such a cloud hold itself together? How did it avoid being swept up and incorporated into the first star-forming galaxies? The prevailing theory is that the unseen scaffolding of the cosmos, the vast web of dark matter, is responsible. These primordial gas clouds would have been the first things to collapse into the immense gravitational wells created by clumps of dark matter, known as dark matter halos. This cloud, therefore, is not just a sample of primordial gas. It is likely one of the very first building blocks of a galaxy caught in a state of arrested development. We are witnessing, for the first time, one of the foundational bricks of the cosmic city before it was ever assembled. By studying its density, its temperature, and its internal motions, all information subtly encoded in the light that Webb so precisely captured, we can test our theories about how dark matter interacts with normal matter on the smallest cosmic scales. Perhaps this cloud is colder than we expected, or more turbulent, hinting at properties of dark matter that are not accounted for in our standard models. Each new piece of information extracted from this single spectrum is a clue, a piece of a puzzle 13 billion years in the making. Let us pause to consider the sheer temporal vertigo of this discovery. The light from the background quasar that illuminated this cloud began its journey when the universe was less than 1 billion years old. During its multi-billion-year trek towards us, continents drifted on Earth, mountains rose and fell, the dinosaurs evolved and were extinguished, and the whole of human civilization flickered into existence. That ancient light, carrying the spectral shadow of this primordial gas, finally arrived at a tiny, golden instrument, purposefully placed in its path by a species that had only just learned to look up at the sky. Through this incredible convergence of cosmic chance and human determination, we have reached back and touched a piece of our own cosmic ancestry, because this is, in the most literal sense, where we come from. The story of the universe is our story. The atoms in our bodies, the carbon in our DNA, the calcium in our bones, the iron in our blood were not created in the Big Bang. They were forged in the hearts of stars. Those first monstrous population 3 stars, whose existence was only theoretical until now, were the genesis of chemical complexity. They lived and died to create the elements that make us possible. And this cloud that Webb has found is the before picture. It is the raw material, the pristine canvas upon which the story of life would eventually be painted. It is the universe's memory of a time before complexity, a time before stars, a time before us. The implications of this discovery will ripple through the fields of cosmology and astrophysics for decades. It provides the first direct observational evidence of the fuel for the first stars. Astronomers can now refine their models of how these population 3 stars ignited. Did they form in isolation, or in small clusters within these pristine gas clouds? How efficiently did they convert this raw gas into starlight and heavy elements? By finding more of these cosmic fossils, and Webb is now undertaking a systematic search for them, we can begin to build a statistical picture of the end of the cosmic dark ages. We can map out how the universe was reionized, how the lights came on across the cosmos, not with a single switch, but as a slowly spreading dawn, galaxy by galaxy, star by star. This discovery is also a profound reminder of the power of looking at the universe in a new light. For centuries, our vision was limited to the narrow band of visible light that our eyes can perceive. Then, we built instruments to see in radio waves, in X-rays, in gamma rays, each new window revealing a cosmos more violent, more dynamic, and more wondrous than we had ever imagined. Now, with Webb's mastery of the infrared, we have opened the final great observational window onto our cosmic origins. We are, for the first time, conducting cosmic archaeology, not with shovels and brushes, but with spectrographs and cryocoolers. We are unearthing the foundations of reality. The narrative of science is one of incrementally peeling back layers of ignorance. When Galileo first turned his telescope to the heavens, he shattered the celestial spheres and revealed a clockwork solar system. When Hubble pointed his namesake telescope at a faint smudge of light and proved it was a distant galaxy, he shattered our conception of the Milky Way as the entirety of existence. He revealed a universe of countless islands of stars. Each discovery made the universe larger, older, and stranger, and in doing so, it refined our place within it. We went from being the center of everything to being inhabitants of a typical planet, orbiting a typical star in a typical galaxy among hundreds of billions. But the discovery of this primordial cloud does something different. It doesn't just push our cosmic horizons further away, it connects us more intimately to the very beginning. It closes a loop in our understanding. It shows us the direct ancestral material from which everything we know emerged. It is a tangible link to the Big Bang, a whisper from the dawn made audible. The universe, through the patient, golden eye of the James Webb Space Telescope, is beginning to remember its own birth. And we, a curious species on a small blue dot, are the ones listening. We are the consciousness that the universe has developed to piece together its own fragmented autobiography. What other memories lie dormant in the darkness, waiting to be reawakened? This discovery is not an end, but a beginning. It is the key to a door we never knew we could unlock. Behind that door lies the story of the first black holes, the assembly of the first galactic seeds, and perhaps answers to the ultimate mysteries of dark matter and dark energy. The universe has been holding on to its secrets for nearly 14 billion years. It has kept a diary written in the language of light, its earliest pages faded and stretched by the expansion of space-time. Now, at last, we have built the machine that can read it. The silent, frozen vigil of the James Webb Space Telescope continues, a million miles from home. Its gaze is fixed upon the deepest, darkest patches of the sky, hunting for the faintest, oldest photons. It is searching for more of these echoes from the beginning, more fragments of the universe's lost memory. Each new spectrum, each new image, is another sentence on a once blank page. We are living in the age when the first chapter of the cosmic story is finally being written, and the tale it tells is more magnificent, more intricate, and more deeply connected to our own existence than we could have ever dared to dream. The darkness is no longer empty. It is filled with the ghosts of creation, and for the first time, we can see them.